Good morning, good afternoon, or good evening, everybody. Welcome to our brand new unit, Unit 9, Energy. I'm excited to get started, so we're going to go ahead and jump right into it. Now, here are the objectives that we'll be covering for the rest of this unit. So please pause the video, take a moment to read through these objectives so you know what to expect as we move forward. All right, let's jump into our first lesson, Lesson 9.1, which is also called Energy. And let's start off with the definition of energy. The definition for energy is the ability to do work and to cause change. And that might be kind of a vague definition, but it's really hard to say exactly what energy is. It's like the wind. We can see the effect that energy has on things, like we can see the effect that the wind has on things, but we can't really see the wind itself. All right, so in energy it's the same way. We can't really see energy directly, but we can see what energy does. So how do we measure energy? Because we have to have a way to measure everything. Well, the unit that we use to measure energy is called a joule, Joule, and we abbreviate it with a capital J. Now, the joule is named after this guy with the fantastic beard, James Prescott Joule. And it is the same as a Newton times a meter, or if you want to use base units, a kilogram times a meter squared per second squared. But you don't have to worry about remembering this long, ugly unit here. We're not going to use it very much. We'll use joules, but just keep in mind, if you see a kilogram multiplied by a meter squared per second squared, that's the same thing as a joule, and it is a unit used to measure energy. There are many different forms of energy, too many forms of energy to list in one short PowerPoint, or even if we had all day. So we'll kind of boil it down to 6 main forms of energy. And to remember what these forms of energy are, remember the word cement, where each letter in the word cement stands for a different form of energy. So C for chemical, E for electrical, M for mechanical, E for electromagnetic, N for nuclear, and T for thermal. And as we go through the rest of this unit and the units that come after it, we'll be talking about different forms of energy. Next up, let's talk about the law of conservation of energy. Now, the law of conservation of energy says that if you have a closed system, which basically just means like a system that no energy can go into or get out of. So imagine a room that's just sealed up super tight and it has some sort of absorbing material where energy cannot leave the room and it cannot come into the room. We would call that a closed system. And what we're saying is that inside that room, the total amount of energy is going to stay the same. Now, you can have energy changing from one form to another. That's fine, but you can never have any energy being created or destroyed inside this closed system. Now, if energy is allowed to come into the room or move out of the room, then it's not a closed system, and the law of conservation of energy might not necessarily be true for that particular room. So here's an example of a closed system. We'll imagine that this box absolutely prevents all energy from leaving or entering the box. So whatever energy is inside the box will stay there, and whatever energy is outside the box will stay outside the box. Now imagine there's a battery inside the box, and the battery is hooked up by wires to a light bulb, and there's a thermometer to measure the temperature of the walls, the inside walls of the box. Now if the battery stores up chemical energy, then it converts that to electrical energy. Electrical energy powers the light bulbs, which converts it into electromagnetic energy, which light is just a form of electromagnetic energy. And then the light will strike the walls of the box and cause the inside of the box to get hotter. So that's thermal energy. We have a lesson all about thermal energy coming up in a couple of days. But the point that I'm trying to make here is that no matter how many times the energy changes forms, the total amount of energy inside the box is going to stay the same. That's the law of conservation of energy. So let's focus on mechanical energy. Now, mechanical energy we can break down into 2 subcategories called kinetic energy, energy of movement or motion, and potential energy, which is energy of position. And you may have heard of these forms of energy before. If you have, that's great. If not, they're just 2 smaller types of energy that put together give us mechanical energy. Kinetic energy is abbreviated by a capital K, so at least that makes sense, right? To calculate an object's mechanical energy, You take 1/2 of its mass and multiply by the velocity squared. So before we go any further, let's take just a quick moment. Let's do a quick math review. What does it mean when we square a number? Well, squaring a number, just means multiplying that number by itself. So 5 squared is 5 times 5, which is 25. 5 squared is equal to 25. 8 squared is 8 times 8, which is equal to 64. Now, I bet you already knew that, but I just like to mention it so that we know that 5 squared is not the same as 5 times 2, which is 10. 5 squared is 5 times 5. Right? So just so we're aware of what it means when we say squaring a number, because we will see that when we do some calculations involving kinetic energy, which is exactly what we're going to do right now. What is the kinetic energy of a 4 kilogram remote control car moving at 7 meters per second? Let's use the guess method to figure this out. We'll start with what is given. You're given that the mass of the car is 4 kilograms, so write down m equals 4 kg, and the velocity of the car is equal to 7 meters per second. What is unknown? Well, it's asking us to find the kinetic energy, so we don't know the value of k. I need an equation that will give me the value of k when I know mv, and so that's where the kinetic energy formula comes in. Next, I substitute. For m, I'm going to replace that with 4 kilograms, and for v, I'm going to replace that with 7 meters per second. Now, when we solve this equation, don't forget we have to take half of the mass, so half of 4 is 2, and then we have to square the velocity. So 7 squared is 7 times 7, or 49. It's not 7 times 2, it's 7 times 7. So we're going to wind up with 2 times 49, which is 98. And then for the unit, we get joules. Where do we get joules from this? Well, we have kilograms times, and then meters per second, they get squared as well. So meters squared per second squared. And remember what we said? A kilogram times a meter squared per second squared, that's a joule. So we can just write J instead of writing out all that crazy complicated unit. Now, something that's important to understand is that if the mass of an object increases but the velocity stays the same, then the kinetic energy goes up, but it just goes up in a straight line. So if you double the mass, for example, then you double the kinetic energy as long as the velocity stays the same. But if the velocity goes up while the mass stays the same, the kinetic energy goes up a whole lot faster. And that's because, remember, when you calculate kinetic energy, the velocity gets squared. So whatever happens to the velocity, the square of that happens to the kinetic energy. If we double the velocity, then the kinetic energy goes up times 4, because 2 squared is 4. If we triple the velocity, the kinetic energy goes up times 9, because 3 squared is 9. All right, next let's talk about potential energy. Well, we had it too good. Kinetic energy symbolized by the letter K. Okay, that makes perfect sense. Potential energy symbolized by the letter U. I don't know, folks. You just have to get used to the fact that in physics, a lot of times we have symbols that don't look anything like the thing that they stand for. Okay, so potential energy is U. Potential energy is equal to mass times gravity times height. So if you want to calculate the potential energy for an object, you have to take its mass multiplied by the gravity, which on Earth, remember, is 9.81 meters per second squared, and then multiply that by the height. Not how tall it is, but how far it is above the ground. So suppose we have a flower pot that has a mass of 2 kilograms and is sitting on a windowsill 3 meters above the ground. We want to calculate the flower pot's potential energy, so we don't know the value of U. The equation we'll use is U is equal to m times g times h. And substituting in, we'll replace the m with 2 kilograms, replace the g with 9.81 meters per second squared, because this flower pot is on Earth and not on Mars or the Moon, where g would have a different value, and replace h with 3 meters. And then you just take your trusty calculator, you multiply those 3 numbers together, and you're going to get k is equal to 58.86. That should be U, actually, so my mistake, I put in the wrong letter there. U is equal to 58.86, and it's going to be joules. kilograms times meters per second squared, and then we multiply another meter, so it's meters squared per second squared, and that gives us joules. Now, remember we said that energy is conserved, and if we take away friction, then mechanical energy is also conserved, which means as an object moves through space or through the air, it will be transforming potential energy into kinetic energy, but the total amount of mechanical energy will always stay the same. So if it loses kinetic energy, then it will gain potential energy, or if it loses potential energy, then it will gain kinetic energy. All right, so take a look at this pendulum. As the pendulum swings back and forth, as it swings to the bottom, it speeds up. So what type of energy is it gaining as it speeds up? That's right, it's gaining kinetic energy. And as it moves to the top of each swing, it slows down, but it gets higher. So what type of energy is it gaining as it gets higher? That's right, potential energy. So as the pendulum moves to the top of each swing, it is losing kinetic energy because it's slowing down, see slow down, but it is gaining potential energy because it's getting higher. And as it moves to the bottom of each swing, it is gaining kinetic energy because it's speeding up, but losing potential energy because it's getting lower. And as it goes back and forth, the amount of kinetic energy and potential energy are constantly converting back and forth, but the total amount of mechanical energy is staying the same. Now, this is a magical pendulum that is ignoring air resistance. In real life, as a pendulum swings back and forth, it has to push the air out of the way, and that takes away some of its energy, moving the air out of the way. And so in real life, the pendulum would eventually slow down and get slower and slower and would eventually stop. It would lose all of its mechanical energy. But in this situation, we're pretending that air resistance is not a thing, and so the mechanical energy stays the same forever and ever and ever, or at least until I stop the animation. All right, so that is it for lesson 9.1, energy, folks. I am so glad you joined me today, and thank you so much for your time and attention. Please come back tomorrow when we will be moving into lesson 9.2, which is all about work and power. So we will talk about what those words mean, at least in a physics sense, tomorrow. In the meantime, please hop on over to Google Classroom. I will have a very short assignment up there for you to do. And as always, continue to take care of yourself, wash your hands, look after yourselves. I hope you have a great day. I'll see you tomorrow. Bye.